Okay, never have your cell phone on when you're in the Math in the House studios. Okay, so this next problem, we've got the curve y equals the square root of x, or f of x equals square root of x. And they want the slopes at 3 points, 1, 1, 4, 2, and 9, 3. Now notice, you can see the slope at 1, 1 is going to be steeper than it is at 4, 2, and that's going to be steeper than it is at 9, 3. The curve gets less and less steep as you go on. So what we're going to do is we're going to evaluate it in general first. Okay, so the slope anywhere is going to be the limit as x, or as h approaches 0, of f of x plus h, now, or f of a plus h, minus f of a all over h. Now, this function is the square root of x. So basically this means it's the limit as h approaches 0 of the square root of a plus h minus the square root of a all over h. Now here's the thing. We're leaving this a because we've got a equals 1, a equals 4, a equals 9. So I don't want to have to do 3 separate times with 3 separate numbers. So we're just going to do the whole thing with a's in it. So now, how do we get rid of, well, let's do one thing here. Let's evaluate it when h equals 0. So I'm going to plug in 0 for h, and I get square root of a minus square root of a is 0 over 0 for h. 0 over 0 can't be defined, so what we need to do is we need to fix this. So we're going to multiply by the conjugate on top because I'm trying to get rid of radicals. So I'm going to say multiply by the square root of a plus h plus the square root of a all over square root of a plus h plus square root of a. Now, on top I have a minus b times a plus b, which is going to equal a squared minus b squared. So I've got a plus h minus a squared minus b squared, all over h times the quantity, square root of a plus h plus square root of a. Okay, now this becomes a minus a on top, which is just an h on top. So I've got h over h times the quantity, square root of a plus h plus square root of a. All right, so what should we do now? Well, I would say we should get the h out of here. Get the h out of here? Okay, so that's what we did. We cancel our h's, and now we have the slope equals the limit as h approaches 0 of 1 over square root of a plus h plus square root of a. Now, if we let h approach 0 here, we've got square root of a plus square root of a is 2 square root of a. So the slope is going to equal 1 over 2 square root of a. And if I multiply by square root of a over a, or square root of a over square root of a, then I end up with square root of a over 2a. All right, so that means the slope right here at x equals 1 is going to be 1 over 2. The slope right here, the slope right here at x equals 4 is going to be 2 over 8, which is 1/4. And the slope right here at x equals 10, or x equals 9, I mean, is going to be 3 over 18, which is 1/6. Is that what the book got? Hopefully it is, because it's always nice when the book is right. Yeah, that's it. Okay, so notice all we do is we stick with our basic definition, which you've all memorized by now, and we plug in the function. So if you know f of x, then you know what f of a plus h is, and you know what f of a is. And so then we just crank this on down, just like we've been doing with evaluating limits up to this point. And when we get to the point where we actually can plug in h, now we have our slope in terms of a, so you can plug in any a values you want. All right, last thing is our using this rate of change in terms of some other function, like velocity. So take a look at, we're just going to arm wave this one. Okay. Yeah, wait, we didn't even want this. Okay, we're back to live action now. Okay, so take a look at example 4. Suppose, that's the favorite word to start a word problem. Suppose a ball is dropped from upper observation deck of the CN tower 450 meters above the ground. What's the velocity of the ball after 5 seconds? Now, this is not asking what's the average velocity of the ball. This is asking for the instantaneous velocity of the ball right at 5 seconds. Okay, then what you do then is you say S, displacement, is 4.9 t squared. Now, if you know, that's because gravity is 9.8, actually 9.81 meters per second squared. So that's how you get, if you haven't had physics, then that would be a mystery to you. But we just say, all right, there's our displacement function is 4.9 t squared. So if we want the velocity after some number of seconds, a seconds, notice they're doing this in terms of a also. You could just plug a 5 in for a if you wanted to. But they're saying, okay, f of a plus h. Well, you plug in a plus h into the 4.9 t squared. So really on top, it's t sub 2 minus t sub 1. So t sub 2 is the 4.9 a plus h quantity squared minus 4.9 a squared. And not t sub 2 minus t sub 1. On top, it's s sub 2 minus s sub 1. So it's one displacement minus another over the change in time, which is h approaching 0. So the change in time is basically 0 because we want the velocity at 1 instant in time. Okay, so let's just crank this out. When you expand your a plus h quantity squared, you have a squared plus 2ah plus h squared. And notice what's happening then is the a squareds get canceled out, and you're left with 4.9 times 2ah plus h squared, because a squared minus a squared is 0. Now, next thing that happens is you can cancel an h, or, like I said before, get the h out of there. And so we cancel our h's, and you end up with 4.9 times 0.2a plus h. Now when you let h approach 0, just plug in 0 for h, you get 4.9 times 2a, which is 9.8a. So the velocity after 5 seconds is going to be 9.8 times 5. The velocity after any number of seconds will just be that time times 9.8. So we know that our ball, if there were no air resistance, would be 49 meters per second, right at the instant of 5 seconds. And then how fast is it traveling when it hits the ground? Well, now all we do is we plug in 450 feet for the distance, and that equals 4.9 t squared. And so you plug those values in, and you end up with about 94 meters per second. So the other rates of change, if we're talking about change in y over change in x, or change in distance divided by change in time, or change in temperature divided by change in time, any kind of function that's changing its value in a given time is going to fall into this situation. And so remember, what we're doing is we're finding the slope of the tangent. Now, if we do that by evaluating the limits, we have it exactly. But what they're showing you in Figure 8 is you can also do it by evaluating the slope of the tangent graphically. Just draw the tangent on your graph, pick 2 points on that tangent, and go y2 minus y1 over x2 minus x1 and get your slope. And that gives you the slope of the tangent. So that is it. Have fun with these.